So now I'd like to call Luísa Carrilho Graça, who is the session moderator. The session is Other Marine Business Opportunities. So Luísa.
Yes, hi Carolina, good morning.
Good morning. So
okay.
The microphone is yours, and well, I wish you all a very good session.
Thank you very much, Carolina. Thank you also to WavEC Offshore Renewables for inviting me to moderate this interesting session about other marine business opportunities. Since we are, I think, a bit behind schedule, I will go ahead and introduce our first speaker, Nuno of TechnipFMC. So Nuno began his career as a structural engineer in the construction business, spent 12 years in Norway working in oil and gas subsea production systems, and returned to Portugal to support energy transition through TechnipFMC New Energy Ventures. Nuno will speak about offshore large-scale hydrogen production and distribution. Nuno, please go ahead.
Thank you, Luísa. Me. Okay. Just to confirm, you're seeing the main presentation screen, correct?
Yes.
Okay, thank you. So, good morning, good afternoon, all. I'm here to explain what TechnipFMC is doing within the energy transition space. As is mentioned here, the New Energy Ventures, it's a new global business unit that was created officially from this year, from November. First, it's recent, but we have been working within this energy transition space for a while, at least since 2016. So TechnipFMC has been operating in the subsea production systems and on the surface systems, providing a different number of services to our customers within the oil and gas space so far, working as an EPCI type of supplier, so engineering, procurement, construction, and installation due to our fleet of vessels that we have, but also performing other specific types of work within FEED studies and especially targeting surf activities such as umbilicals and flexibles. As we advance to the energy transition space, the strategy has landed in these 4 pillars that you are able to see here. So basically, we are utilizing our expertise as a system integrator provider, and we are combining all the legacy technology that we have from the past and apply it currently into the energy transition space. So these 4 pillars that we have shown, we started by the carbon capture and the platform electrification, where we partnering with our existing clients from oil and gas to decarbon the offshore or upstream segment. We also entered into the offshore wind, where we partnering with developers to optimize the offshore wind development. So here we play a role within the EPCI, the front end type of engineering, systems engineering integration, offshore construction, pipeline type of technology work. We establish, for example, a partnership with Magnora to target the Scandinavian type of licensing and tendering that are ongoing. Also, within the WavEC and Tidal, there has been some partnering with Bombora and with Orbital Maritime Power in order to capture some interesting developments that we have been having within this space. But now I'll focus on the last one, the green hydrogen. That is the topic for today's discussion. So basically, we partnering with industry leaders to commercialize and develop green hydrogen through the Deep Purple concept. as most of you already know, the hydrogen will be playing a major role as enabler for the energy transition. And we need to tackle this enormous need that we will be facing going forward. On the optimistic forecast, it's expected that we will have around 24% need within 2050. And the cumulative investment expected from renewable hydrogen in Europe alone will go up to 470 billion euros. So the Deep Purple system was developed by TechnipFMC, which with the clients and key partners using the wind energy to produce and distribute green hydrogen to use or be a stable delivery power, to act as a local energy production, to tackle the necessity to reduce the carbon emissions, to be competitive with the cable power to shore, and to target a large-scale offshore renewable hydrogen production. I'll try to put the video on. Just let me know if there's no sound, please.
Hi, Nuno. I am not hearing the sound.
Okay. Let me go back then. One more try.
Offshore wind is intermittent by nature and will often not match the demand for energy. Turning offshore wind into a stable energy source to meet demand is where Deep Purple finds its place. By combining offshore wind, hydrogen production, and subsea hydrogen storage, hydrogen is used as a buffer to stabilize the energy supply. So how is this accomplished? Depending on wind conditions, Deep Purple will find the optimal windows to produce hydrogen, store it, and re-electrify it. As shown here, wind energy is highly intermittent. The black line shows the energy demand. In periods with sufficient wind, electricity created from the wind turbines is delivered directly to the consumer. Deep Purple uses the excess electricity to produce hydrogen. Producing hydrogen requires electricity and fresh water for the electrolysis process. The electricity comes from the wind turbines. Seawater is purified by filtration, reverse osmosis, and deionization before going through the electrolysis process, where the water is split into hydrogen and oxygen. The hydrogen is then compressed and transferred to standardized storage units on the seabed. The subsea hydrogen storage can be scaled according to need and can store energy volumes much larger than any existing battery. In periods with weak or no wind, hydrogen is converted back to electricity through fuel cells. Hence, electricity will also be delivered to the consumer when there is no wind. The consumer might be offshore oil and gas installations needing renewable electricity to decarbonize the operation, or remote islands not connected to the grid currently, running on fossil fuels. The Deep Purple system can also deliver hydrogen on demand to hard-to-abate industries like steel and fertilizer plants, and the subsea storage can be used for large-scale, safe storage of hydrogen in harbours for the maritime sector. At the core of Deep Purple is the energy management system. All actions are measured and tracked to optimize the production, storage, grid stability, system utilization, maintenance, and cost of energy. The complexity of this is high. Understanding all aspects of the system, including weather, load demands, availability targets, and equipment characteristics, is fundamental, and managing it all is required in order to deliver stable energy at the lowest cost.
So to recapture here a bit, the the Deep Purple concept and process. So offshore wind is an intermediate in nature, and in many ends, the user needs a stable power to supply on the decarbonization of their operations. So by combining the offshore wind with the hydrogen, we actually use the hydrogen as a buffer to both store and to stabilize the wind production. In the periods where we have good wind conditions, the electricity created from the wind turbines is delivered directly to the consumer. Excess power is used to produce hydrogen. For the hydrogen production to take place, we will use the pure water. So this has to go through a treatment from the seawater that is extracted, goes through a purification treatment, and then it's added to the electrolyzer systems. Through the electrolyzers, the hydrogen is extracted, compressed, and transported into the hydrogen flow, either through to a hydrogen grid system or to a subsea pressurized system that we have. Where we have periods with low wind conditions or no wind, the hydrogen then is electrified back through fuel cells, and we further deliver to the consumer. So in this way, we have a stable delivery of power to the consumer all year around. Like mentioned in the video, the potential markets here that we are looking at, we see this span of ocean space. So on one side, we have the off-grid energy systems, while on the other side, the large-scale hydrogen production and storage. In the off-grid energy systems, delivering renewable and stable power to traditional energy installations and remote islands. This opportunity linked to the market are primarily driven by the need to decarbonization. For example, replacing gas turbines and diesel generation sets. By combining this offshore wind and hydrogen, we can enable 80 to 100% reduction in emissions. For the offshore green hydrogen production and subsea infrastructure for coastal application, here we have the offshore hydrogen production that will enable the harvesting of wind resources far from shore, where the transport of electricity could be a challenging thing. So the hydrogen pipeline here offers up to 10 times more capacity for energy transfer compared to a power cable, and our subsea storage system can be used to store large amounts of hydrogen. For the current ongoing applications of the Deep Purple, so we started this year on the Deep Purple pilot, and it will continue over the next 2 years, where the project consortium will design, build, and test a physical land-based pilot at TechnipFMC Norwegian headquarters in Kongsberg. The pilot will include an electrolyzer, hydrogen storage, a fuel cell, energy control system, as well as the development and testing of advanced control and advisory system and dynamic process simulator. The pilot will allow the consortium partners to ensure an energy efficiency and an autonomous operation offshore, as well prepare the system for large-scale offshore commercial use. This has been object for governmental funding, and the partners are described here, going through Vattenfall, Repsol, Nel, ABB, among the NV and other Norwegian partners. Other ongoing initiative is the floating power plant, where we are working with this Danish company to develop a combined floating wave and hydrogen energy storage system. So it's a self-contained floating power station that will use hydrogen process technology to manage wind wave intermittency. So this is a decentralized type of concept, a standalone, that could capture the full system, going from the production to the storage part of it. And last, we have just finalized in October this concept study that we did together with EDP, SEIA, WavEC, and the University of Southeast Norway, where we studied an innovation and modular solution for hydrogen production from offshore wind energy for multiple end users to be deployed worldwide, producing and transferring hydrogen in large scale for decarbonization of the economy while handling the wind energy intermittency. So the Beyond project, as mentioned, consists on developing the concept of two concepts actually. One that we are seeing here in the picture, a centralized concept where all the production units for the electrolyzer are concentrated in one platform, but we also target on the decentralized concept where each unit, as shown before on the floating power plant, can work independently out of the system. Of course, this implies to have a subsea infrastructure, pipeline, collecting manifold, and then piping to shore. And we consider different scenarios on the full hydrogen production and on the 60% hydrogen production plus electricity. In the end, the target was to have this modular solution for large-scale offshore hydrogen production from the wind energy, standardized for every end use. So we were not targeting any type of floating concept. We kept it agnostic. We tried to have a system that could fit the different concepts that are being studied. In parallel, it can comprise also of the storage and export hydrogen in a pipeline. So either we storage in the modules that we have within the Deep Purple, or use the pipeline as a buffer as a buffering storage. Centralized and decentralized solution, as I mentioned, and this, of course, supported by techno-economic modeling, market analysis, and roadmap for commercialization. And with this, I conclude my presentation. Thank you.
Thank you very much, Nuno. That was very interesting. Now we move on to the next speaker. So Hiroshi Kimura of Iwatani Corporation. I hope I'm pronouncing it correctly. So Iwatani is a leading hydrogen supplier in Japan, currently operating 53 hydrogen stations in Japan and 4 in the US. Hiroshi Kimura is in charge of managing and expanding hydrogen business globally and will speak about hydrogen storage technology and hydrogen stations.
Thank you, Luísa. Can you see my screen?
Yes, perfectly.
Yes. Yeah. Hello, everyone. My name is Hiroshi Kimura with Iwatani Corporation, Japan. I'm a Deputy General Manager of Hydro Division, and I'm responsible for building a global hydrogen supply chain. I really hope I can explore the opportunity to import hydrogen from Portugal to Japan in the future. So can you see my screen still? Okay, yeah. So let me introduce who we are. Iwatani Corporation is focusing on gas and energy, and we are the top supplier of LPG gas and hydrogen in Japan, with the net sales $6.3 billion. And also we are a public company listed in Tokyo Exchange stock market. This is our history of hydrogen. We started the hydrogen business in 1941, 80 years ago. We are the first company to sell hydrogen in Japan, and also in 1978 we became the first Japanese liquefied hydrogen producer in Japan. And still now, we are the only one and the producer of hydrogen of liquefied gas. So therefore, our market share of liquefied hydrogen in Japan is 100%. And then including gaseous hydrogen and liquefied hydrogen, our market share is 70% in Japan. So we are proud of 80 years of experience for safety and also the dominant market share in Japan. So we have the 3 liquefied hydrogen plants in Japan, Osaka, Chiba, Yamaguchi, and total supply capacity, the 30 tons per day. In addition to these capacity, we have the 8 compressed gaseous hydrogen plants as well. And Iwatani became the first hydrogen refueling station in Japan 7 years ago. And now we are currently operating 53 stations in Japan. And also Iwatani is operating 4 stations in California, USA, and are going to increase to 23 stations by 2024. Iwatani is the largest station operator in Japan, and number 3 in California in 2024. October 2020 is the milestone for decarbonization movement in Japan. The Japanese, the former Prime Minister declared carbon neutral by 2050. Since then, hydrogen has been attracting more attention than before because the hydrogen could be a key factor to realize carbon neutral. This is the roadmap by Japanese government green strategy. The demand for hydrogen will be increased to 3 million tons in 2030, and then 20 billion tons in 2050. But the price target is coming down from $3 per kg in 2030 to $2 per kg in 2050. So 20 million new demands will be going to mainly 3 sectors. One of them is the power plants. Japan still have the many oil power plants. So therefore, Japanese government suggested the electricity power company to use hydrogen or ammonia to co-fire with coal to minimize the CO2, the emissions. And the mobility sectors, as I explained to you, we are supplier of hydrogen to most of the hydrogen stations. But in the future, heavy-duty trucks will be our main target. So there's 5 to 6 million tons per year will be necessary to fit the needs for heavy-duty, the supply. And also the steel industry, in order to realize the carbon neutral, they need hydrogen for the production. So we're expecting 7 billion tons per year in the future in Japan. So this is what we are going to do, from the next year, 5 to 10 years. Currently, we are producing hydrogen from the fossil fuels like LNG, but we are going to build global supply chain of CO2-free hydrogen sources. Currently, this is a very small, small-scale demonstration project funded by the Japanese government. Iwatani and Kawasaki, also Marubeni, will get together to small-scale demonstration. We have already built the special ship tanker to import the hydrogen from Australia to Japan. We also set up the tanks in Kobe in Japan for storage of the liquefied hydrogen. And recently, Iwatani and Kawasaki Heavy and Ineos were awarded much larger scale demonstration for liquefied hydrogen supply chain. For invest, for coming 10 years, it will be about $3 billion, and the Japanese government will support us the $2.2 billion. What we should do is to build larger scale the development of the liquefied hydrogen importing from overseas countries. Currently, as I said, we have a small scale ship, a tanker, but for the full scale demonstration, we need the special tanker 128 times larger than current one. And also the storage tank in Japan should have the 20 times larger than the current size. So we are now demonstrating the importing from Australia or some other, but we are going to increase the opportunity to build the global supply chain, hopefully from the Portugal as well. This is just for your reference. We are currently designing fuel cell ships, which will be operated for Osaka Kansai Expo in 2025. So Iwatani, as a leader of supplier of Japan, we try to create more demand for hydrogen. Also, they would like to build the global hydrogen supply chain, hopefully from the Portugal. We expect the offshore, hydrogen, production in Portugal, and hopefully we would like to explore the more opportunity to the import of the hydrogen from Portugal to Japan in the future. Thanks so much for your attention. Thank you. That's all.
Thank you very much, Hiroshi Kimura. Thank you. So let's move on to the next speaker. We are running a bit behind schedule. So José Chambel Leitão of Hidromod. I'll introduce José. He has 30 years of experience in consulting, operations services, and research and development. Has worked in connection with sea waves, hydrodynamics, transport processes, hydrology, and river basin management. José is a managing partner at Hidromod and a non-executive director at WavEC, and will tell us about ICT tools for the management of ocean resources. José, good morning, and please go ahead.
Okay, thank you. I think it's getting through the screen.
Yes, it is.
Okay, thank you. Okay, thank you for this opportunity. I want to thank WavEC for the opportunity of being here and showing some of the things we've been doing and some of our thoughts on this field. I'm from a small company. We are 17 people. We are based in Lisbon. We are one of the associates of WavEC, and we do mostly numerical modeling and information technologies, data management, and things like that. I'm going to focus on on a perspective on how to deal with data and the ICT perspective, meaning information technologies and communication. And the perspective, I think it's this: how to get the right data to the right people at the right time. So this is one concern we have at the company when we deal with this subject. And here, focusing on marine energy, we usually data must be focused on one of these topics. So site characterization, environmental assessment, energy resource evaluation, construction, operation and maintenance. I'm going to talk a bit on these issues and focusing on this, and what are the existing tools, and of course mainly the tools that we have, the tools that we use, and what we've deployed so far that might be useful for other people. I've gathered a few things, and mostly based on these two sites that were already referred in some of the presentations. So the site of Viana do Castelo, where the Wind Float Atlantic is based, and the site of Aguçadora, where now we will have the high wave from Core Power, but previously there were other projects on this site. So we really, our main concern is how do we get the right data to the right people in the right time, to the people that are involved in these sites. How do they get their data? How do we share data to other people that want to study opportunities in these sites? So how do we do this? There are a number of equipment there, and there has been a number of equipment in that area for a few years now, and this equipment is there due to this specific equipment I'm showing here is there due to the Instituto Hidrográfico. So they maintain a host of equipments there in the sea and on land. So tide gauges, wave buoys, and it is very important that this data gets through to the people that needs it. Okay. But there are other information. These are numerical models we have at the company. We have numerical models running for the site. This is Viana do Castelo, so this is a current hydrodynamic model operational for the site of Viana do Castelo. It has the ocean influence, and it has the river flow influence, and so it is permanently calculating the sea level and the currents, and this is similarly a wave model. So it is permanently calculating the waves for the area of Viana do Castelo, and there are meteorological models. So this is a model we use for wind also in that area. It's a larger area in the north of Portugal. So this is another other data sources for that area of those two test sites, and these data we already send these data to ports, for instance, to the port of Leixões and to the port of Viana do Castelo, and we already try to simplify the data so that it gets, in this case, it's a public page that is being provided to the public, but also used for port operations. So this is an example of how to get this data to and format it as the people in the ports think they need it. Okay. This is another example. This is the data that exists for the site of Viana do Castelo. This is from the environmental assessment from the public consultation. So this data is there. The geology chart, the shallow geology chart, for instance, for the site of Viana do Castelo, and this is from the public consultation, and this is also some of the data that is quite needed when planning this kind of projects. Similarly, for the site of Aguçadora, there are some sediment charts for the site, and this is also from the public consultation. For the public consultation, the assessment by the public, and so what we want to do is to make this data available as possible to different audiences. Okay, and for this we've and within a number of European projects where we have participated, some of them with WavEC, we've set up a data platform for different test sites in Europe, also those in Portugal, of course, where we have data that is relevant for the projects in these test centers. So this is data it's acoustic data. It's data on birds, on sea mammals, on all that kind of stuff that is important for instance, the environmental assessment of these projects. So this is freely available over the internet. It's a way to channel the information to people that may need it. We have also in the company we've developed the thing that we call our Swiss knife, which is a software that enables us to put historic and operational data, operational meaning forecast, nowcast and forecast for the next few days, which has different components. It has the user interface, security layer, and then it manages data services. It links with the data acquisition, a data lake, a scheduler. So it's a quite sophisticated tool that enables us to manage data that is measured on site, satellite data, numerical models, and then direct this to people as they need it for different operations. Of course, marine energy related operations are one of them. We have existing services right now. I've shown one of them, that Maran Data platform, and we also provide based on these tools. We also provide metocean historic and operational, so nowcast and forecast data for the ports of Leitão, Viana do Castelo, Aveiro, Setúbal, this for about 10 years now. So they've been quite happy with these services we've been providing them. And also for aquacultures, we are providing these kind of services for aquacultures, water utilities, and other industries. And well, I try to keep this as short as possible, and that's it. If you have any questions, I'm more than glad to answer to them afterwards. Thank you.
Thank you very much, José. We will move on to our fourth speaker, Ken Takagi. I'll introduce him. So Ken Takagi, since 2008, has been a professor for ocean technology policy and environment with the University of Tokyo. His research interests relate to marine renewable energy and underwater vehicles. And Ken Takagi is a member of the IEEE Ocean Engineering Society and will speak about research activities on ocean technologies.
Okay, thank you for your kind introduction. And good afternoon, maybe, and good evening, all. It is my great honor to have the opportunity to introduce our research activity of our laboratory. Okay, let me start my presentation. This is a brief introduction of my lab. Name of my lab is Ocean Technology Policy, which belongs to Department of Ocean Technology Policy and the Environment, the University of Tokyo. And our goal is building a sustainable society with ocean technologies. And the current research topics are ocean current turbine, social acceptance of ocean technologies, and cost reduction of the floating offshore wind turbines. Okay, the first topic is ocean current. as you know, the North Hemisphere, there are very large clockwise current. And the current is enhanced at the East Coast because of the Coriolis force. Therefore, the Japan get actually the very large and strong current, strong ocean current. Okay, and another opportunity is that the Japan has 417 populated islands, and we have to supply the electricity to maintain these populations. And therefore, we need some renewable energy sources near these small islands. Okay, so that's the main motivation with ocean current turbines. But we have technology challenges. The first challenge is water depth, which is 100 meters to 1,000 meters. And the other challenge is slow current speed. Actually, the maximum ocean current speed is 2.5 meter per second, which is smaller than the tidal current speed. And therefore, we have to develop the floating type and the large turbine diameters. Okay, this is a brief history of how to develop the ocean current turbines. We started from the small size laboratory experiments from the 2009, and this device is bring into the towing tank test. And fortunately, we succeeded to towing tank test. And then the IHI Corporation took the leadership. And then they built a prototype. And they successfully conducted the real sea test in 2017. Then after, actually, the project is has not big progressive because of the COVID-19, but recently they have done second real sea test. Okay. And the role of university is has been changed to the measurement of the ocean current and simulation of the motion of devices. This is a size of prototype. Actually, the prototype, the output is 100 kilowatts, and that prototype has about 11 meter diameter turbines. And this is the final goal. The rated power will be the 2 megawatts, and the turbine diameter will be more than 40 meters. Okay, and this is a strategy how to expand the market. Starting from the small islands, then we increase the number of devices. At the same time, probably the wind turbine industry prepared many infrastructures, and we are planning to enjoy the infrastructures prepared by the wind turbine industry. We increase the number of farms. And that is our strategy. Okay. Okay, let me move on to the second topic. That is the social acceptance of the marine renewable energies, which is very important as the initial stage of the deploying the marine renewable energies. Actually, as you know, we have traditionally fishery industry as well as transport, surface transportations. So utilizing the marine space in Japan is a little bit complicated because of many stakeholders. Okay, so it is very important to have coexistence strategies. Okay, and we propose several coexistence strategies. And the first one is sharing real-time in-situ oceanographic information from marine renewable energy devices, which is proposed by our laboratory. Then second one is using MRA devices, foundations as fishery support structures and as artificial reefs. Features questioned by several audience in this symposium. The third one is co-location with commercial and leisure activities such as aquacultures. The fourth one is sharing generated electricity for local community to improve the other local industries. The fifth one is utilization of regional resources for construction and the operation of the power farm. Fourth and fifth are very common ideas, I think. And then we performed a questionnaire and interview surveys. This is the result of questionnaire and interview surveys. Then results is very interesting because this is answer by fishery industries. The other answers are getting from other stakeholders. And then the results show that fisheries prefer the ocean information sharing options, while other industries prefer using local resources to create business collaborations. From these results, currently we propose integrated information sharing schemes like this. Actually, the marine renewable energies itself has a data connection with land, and so naturally it is not a difficult task to provide a real-time data from sea. That is a basic idea. Actually, this idea is not commercialized, but currently we are studying on this integration of the sharing schemes. That's all. Thank you very much for your attention.
Thank you very much for your presentation. Let's move on to our last speaker, and then at the end, we still have some time for questions from the audience. So our last speaker would be Francisco Rey Fonseca of WavEC. Francisco is a senior engineer with more than 7 years of experience in offshore renewable energy systems. His work has been focused on resource assessment, prototype testing, and logistics studies for offshore renewable energy projects. Francisco is currently managing and developing a validated decision support tool for offshore operation planning and ocean energy projects with DT Ocean Plus Age 2020 project. Francisco will speak to us about EU scores demonstrating the potential of multi-source offshore renewable energy farms. Francisco, please go ahead.
Can you see my slides now?
Yes.
Okay, perfect. Thanks for the introduction, Luísa. So, as it was said, my name is Francisco Rey Fonseca. Sorry, can you switch the slides? No, I mean the. Okay, never mind. Are you seeing the presented mode or the right slide? It's good. Okay. So, hi. So, as it was said, I'm going to be presenting to you today EU scores. My name is Francisco Rey Fonseca. I'm the offshore operations specialist at WavEC. And EU scores stands for European Scalable Offshore Renewables Energy Sources. It's a European funded project that WavEC is involved in, and that I'm very excited to tell you all about it in the next 10 minutes. So if I can change. So if you're sitting here, I'm confident that you are aware that we're living in this scenario of climate emergency, that we have strict climate targets that we have to meet. And to do so, we'll have to decarbonize our power sector. Offshore renewable energy will play a fundamental role in this sense. But if you're sitting here and if you made it this far in this presentation, in this seminar, then you're probably comfortable with the idea that renewable energy will inevitably expand to offshore environments. And this is because we had some presentations today. We had the chance, the opportunity to hear some more about the technology developers and some of the front runners of the sector. But offshore renewables are essentially very interesting. And this is because in offshore, there's better resource, winds are more constant and have higher speeds, waves transport more energy. There are fewer space limitations, which means that devices can be larger and more powerful, produce more energy. And there are also some lower environmental and social impacts. Now, but as we increase the penetration of renewable energy in the energy mix, we are likely to face some challenges. And these challenges are aggravated if we only focus on mature technologies, on a couple of mature technologies, just like offshore wind. And these challenges, the first one is related to ensuring energy system reliability. Well, this is something that we always hear about, which is related to intermittency of renewable energy. And the point is we need to produce electricity when there is a demand for it, and we have to always meet these factors. The second is related to dealing with competition for space. Now, as we moved offshore, obviously there are less competition for space than onshore. Onshore, for example, for wind, the best sites are already being used, but still offshore, we still face some competing uses, namely aquaculture, shipping, fishing, and other environmentally exclusion zones as such. Also, there is the requirement to ensure that there is sufficient inter-device distances. So this means that for wind turbines, devices must be separated sufficiently in order to not reduce the power generation of the downstream turbines. And as turbines or as devices increase, so does the need to increase the distance to shore. Sorry, the distance between devices. And thirdly, and this challenge is actually related with the other two, is the need to obviously lower the cost of energy generation. And these are some of the advances that some technology developers have been achieving great results in this sense. But we also will have to be able to ensure that essentially renewable energy production is still an attractive business case in the face of curtailment during peak wind times, and also dealing with the interpark effects or shadowing effects that I just mentioned before. Now, what if we combine different sources of offshore renewable energy? Could this be a solution? Well, if we did so, first of all, diversifying the energy mix and introducing coupled technologies such as solar, wind, and waves, well, first of all, this could lead to a more reliable and low-cost energy system. And this is because, and this graph was already shown before by Miguel, but essentially, these phenomena, the environmental phenomena related to sun, the wind, and the waves, they follow cyclic patterns, and those patterns are not in phase. So essentially, by combining different sources, there is, in theory, the potential to produce more reliable and more constant energy throughout time. This would lead to grid balancing, so that would be an attractive service to pursue. And finally, obviously, by producing energy more continuously, that could also impact the sales or the revenues of such a park. Finally, this could also be combined with hydrogen, which is one of the main themes of this seminar today. But so as it was mentioned, hydrogen could be coupled in the system, producing during the times where the electricity demand is low, capturing the energy, the renewable energy that is being produced, and using it to produce hydrogen, either onshore or offshore, in order to sell it later at a revenue. Secondly, by co-locating different sources of energy, and again, sun, wind, and solar, we could achieve a more cost and space-efficient utilization of offshore area. And this is because essentially there is a potential to use the same substations, to use the same cables, the marine space, obviously, and share vessels. all the sharing all this infrastructure has the potential to reduce the costs. So we'll be reducing not only the total space needed, but also the OPEX and the CAPEX related to the project. Now, everything that I just mentioned is essentially the motivation behind U-Scores, which was already briefly mentioned in other presentations. But U-Scores, it's a 4-year European funded project that just started in September. It will last until October 25. It has a total budget of 46 million euros. And the objective is to demonstrate the complementarity of different offshore renewable energy sources, wave, wind, and solar, demonstrate the technical, economic, and also environmental potential of multi-sources offshore renewable energy farms, and finally accelerate the commercial deployment of wave and floating solar PV energy projects. We'll have 2 pilot demonstrations, one in Belgium, which will be a floating solar PV plus an existing fixed offshore wind park. And then we'll have a demonstration as well in Portugal, floating wave with a floating offshore wind, the floating wave being developed by Core Power. The consortium is a cross-country consortium. We have 12 European countries, 17 partners, 8 scale-up advisors, all coordinated by DMEC. But throughout this project, what we expect is to do essentially the de-risking of the technologies. So we'll be achieving technical de-risking, regulatory de-risking, and a financial de-risking. The technical de-risking is firstly demonstrating the technologies offshore solar PV and wave energy, which are a little bit less mature, but also focusing on large-scale design. So in the large-scale design, we'll essentially focus on how this could be scaled in a multi-source farm, and focusing on anchoring and mooring designs, focusing on advanced O&M strategies, namely using autonomous monitoring systems, and also some grid integration plans for multi-source parks. The financial de-risking will be focusing on learning rates, cost reduction in different scenarios, trying to evaluate exactly the business case for different regions in the EU, because in different regions you have different legal frameworks that you have to take into consideration. And then everything will be evaluated and financially assessed in the end. And last but not least, we'll have the regulatory de-risking, and this will be achieved through stakeholder gathering events, in which I hope to see you all. We'll do resource and energy system assessments, and finally, in the end, the objective is also to come up with policy and regulation advice or documents detailing this advice that we found out in the course of the project. Well, this is all for me now. Thank you for your attention, and happy to address some questions that you have.
Thank you very much, Francisco. So we have a few questions from the audience, which is great. And I think it would be interesting to try to address them now. Carolina, please feel free to interrupt me if you think we do not have enough time, but I will just go ahead. So there are a few questions for Nuno of TechnipFMC. The first one is, what is the overall performance of the system starting from hydrogen produced by wind power and the retrieval of electrical energy? Nuno, would you like to address this question?
Yes, thank you. So basically, in terms of efficiency, we have approximately 60% efficiency when converting from electricity to hydrogen, and the same goes on the other way around. So basically, we are talking about a loss of 40% at this point, around 40% on each step. That's why the system itself is dimensioned in such a way that it could store enough hydrogen. Then when doing the reverse electrolysis, it's possible to match the production capacity of a large-scale wind farm. We are talking about 1 gigawatt wind farm.
Okay, thank you, Nuno. Moving on to the next one, also for you. What would be the size of the hydrogen storage? Is there any concern in terms of storing this kind of structure in the seabed?
That is one of the advantages of using storage, subsea storage, because on one hand, if you store it inland onshore, there's some extra safety measures that needs to be in place due to the need to isolate it from oxygen, while underwater it's possible to maintain it in a much safe environment, contained safe environment. Of course, it's stored, even if it's in the coastal line, it's stored near harbors or near more industrial infrastructure facilities. It's not targeting to be stored close to let's say housing or more people type of environment, despite the fact that for one of the cases that it's targeting the coastal island, the isolated islands, it's expected to supply these types of small communities.
Okay, thank you very much, Nuno. I just forgot to mention that the first question was placed by Mário Bruno Ferreira, and this last one, which Nuno just answered, by Lúcio Rodrigues. There is one additional question for you, I think, Nuno, from Pedro Vinagre. What could be the main constraints regarding licensing? If we can say something about that for now. And how do the potential environmental impacts differ from, for example, bottom-based OE devices?
The challenge here is in terms of industrial standards and regulations. There is no specific one. So what we have been using so far, it's a cross-referencing of oil and gas industry standards and regulations, and also some coming from the wind and hydrogen onshore type of regulations. So we are discovering as we go along. That's why DNV is also part of one of our partners in order to help us to certify and support us within the industry regulation part of it, but it's not yet established.
Thank you, Nuno. And there is one last one for you. I'll read it out. How small is the hydrogen pilot system being built? Could you relate the structure to, say, the size of something like a car, a house, or larger? And what hydrogen production quantity could be expected from the small-scale pilot system? Could this small-scale system be used on a mobile platform with storage? This question is from Mike V.
It's one container size. So basically, we are talking about the modules are at the size of one standard container. It's a 60 kilowatt electrolyzer. The output in terms of hydrogen, I don't recall the figure, but I can check it. But we are talking about a small scale pilot yet. So in this case, this pilot that we are starting, it's aimed to have all the management, energy management flow and the control systems qualified in order to understand how it works. So basically, we are doing an emulation type of supply, so replicating a wind farm type of power supply, and we will be testing how the management system and control system will act on this pilot.
Thank you very much, Nuno. There is one additional question which I will place to all speakers, and please feel free to answer if anyone wants to contribute. So, are you able to give some insights as to the motives for developing hydrogen? In particular, what are your views on the development of the infrastructures, and which signals do you perceive on this particular aspect? Japan and Portugal have different constraints and infrastructures, so it would be interesting to understand how they compare. This question is from Benoit Lebeau. So I will invite any of the speakers to contribute to this question. Nuno, would you like to comment on this one since you are on screen now?
I would leave the room for the others to have a word also. Otherwise, I'm just one speaking. So go ahead, anyone.
Let's give them a minute.
Unmute. Unmute. Oh, it's muted. Okay, sorry. So obviously hydrogen is one of the most interesting decarbonization factors. These are all the big words, buzzy words that we hear all the time. We see it as an opportunity to store the excess energy that we produce offshore. I'm not sure if the question is specifically directed to integrating hydrogen in offshore environments, or just a general question for hydrogen itself. But Nuno had a very extensive and great presentation on this, on the advantages of touching the advantages of producing hydrogen offshore, but it's related also with there's some safety issues which are better when you're offshore for storing hydrogen, and the objective is also to mitigate the peaks and the lows of energy production in order to achieve some storage capacity in that sense. Not sure, I'm pretty sure that you want to add stuff to this, but
Thank you very much, Francisco. If any other speaker wants to say something about this topic, let me know. And if not, let's just move to the final question from the audience. We have one more. So the question is from Maria Leonor Domingos. It would be interesting to know what is the life cycle carbon footprint of these different marine renewable energy sources in comparison with onshore solutions. Francisco, would you like to comment on this one?
So in scores, we will essentially do some life cycle assessments to the carbon footprint. This is one of the tasks that will be, and actually WavEC is leading some of the work there. But essentially, there are many studies in this area. This is not exactly my area of expertise, unfortunately. But I'm happy to share more information that we have, even internally at WavEC, with the others.
Okay.
Yes.
Thank you.
Yeah. Can I make a comment?
Right. Yes, please go ahead.
Yeah, of course, carbon life assessment of carbon footprint is very important. But in terms of the life cycle assessment, other important issue is footprint itself. In that sense, the marine renewable energy could be 100% renewable. In that sense, marine renewable energy is has no footprint, and not only the carbon footprint, but also they have no destruction of the nature. That is my comment. Thank you.
Thank you very much, Ken. Anyone wants to add something to this last interesting question? And if not, I will close our session with a big thank you to all speakers for these very interesting presentations. Thank you all.
Thank you.
Thank you so much.
Thank you, Luísa.
Thank you, Luísa. Thank you, all speakers. So now we would like to share a very short video from the Japanese embassy.